Everyone say hi, Ben.
Hi, Ben.
Ben. Which one's Ben?
We are going to make some meaning behind some things that we've been doing. We have done 2 to the third.
It probably does.
We have done
You're young and you know
2 to the 3.5, which I can call 2 to the 7/2. We've done 2 to the 4th. You guys have hopefully started to figure out things like, well, I'll actually call this 3.5, that if I know that 2 to the 3rd is 8, and I know that 2 to the 4th is 16, and I know that 2 to the 3.5 means if this is multiplying by 2, then if I want to go 2 steps, I can actually create a meaning and say, well, let's multiply by 2, but in 2 equal steps, let's multiply by root 2. And I know that this is actually 8 root 2. I can actually get some meaning behind this. And without completely describing that process, I get the idea that there's a partial meaning and linkage between how to get from 3 to 3.5 to 4 as an exponent. Today, I need you to sort of do something that we haven't done a lot of in math, which is to get a little bit abstract with your thinking. Partway between 3 and 3.5 is a number you are very familiar with. You're familiar with this number because sometime next week, ideally, depending on the day, and no, we're not launching into the conversation of how that's going to look right now, we get to celebrate its discovery, although that number should have been 2 pi. Shh. So I know that between 3.5 and 3, we get this number, 2 to the pi. Is it about this?
No,
Yes. So knowing that between 2 to the 3rd and 2 to the pi, I know, I just hear some conversation. I'm like, okay, I know that 2 to the pi has to exist somewhere between 2 to the 3rd and 2 to the 3.5. That's all I'm asking you guys to accept. Can we accept that much? That if I have a graph of all these values at 2 to the x, and I know that this could be a graph of y equals 2 to the x, that somewhere in between this, somewhere in between 2 to the 3rd and 2 to the 3.5, I'd have to hit up every single value of 2 raised to a power. And given that, there's meaning behind this. This is the idea behind real number exponents. And we're going to be working with real number exponents because our rules are going to basically apply and be the same as they always were. Let me give you some examples of how your problems are going to look. 3 to the pi times 3 to the pi plus 3. Now, we're going to try to simplify these as much as we can. I can't approximate them without means and methods that we haven't learned yet. You actually don't learn the method to hand approximate that until much later. You could use them in a calculator and that'd be okay, but we can simplify it down to become one thing. Yes, Noah?
Is the answer 3 to the 2 pi plus 3?
It is 3 to the 2 pi plus 3. Do you know what the common wrong answer is going to be?
3 to the pi squared.
No. People will look at this and want the 3 times 3 to be a 9. They really will. And when you do that, you're not truly thinking about what's happening. So I'm going to go off to the side here and talk about this problem. 3 to the x times 3 to the y. I know 3 times 3 is 9. But 3 times 3 is 9, not because of any reason that you're thinking at the moment. When we're in exponent world, what I want you to think is 3 times 3 is 3 to the 1st times 3 to the 3rd, which gives me 3 to the 1 plus 1. So 3 to the x times 3 to the y is not 9 raised to anything. It's 3 raised to the x plus y. And the rule we're going to use on this, the rule that's been applying to both of them, is multiply same base, add exponent. And you're going to have to tell yourself that several times because there are a lot of ways that that can look a little tricky. For one, depending on how well you did the last assignment, you may not be seeing that they can in fact be the same base. If I take root 3 raised to the x times 3 to the raised to the pi times 3 to the pi plus 3, can we make those have the same base?
Yes.
Okay. No, you had a question?
Yeah, I was just wondering why we're going over stuff that we did last semester.
We're building on it because we're actually doing exponents that are not whole numbers and not rational numbers. And part of the skill that we have to do right now, the big skill we're using is getting things to be in the same base, to express numbers as the same base. Yes, Garrett?
So for this, would we subtract 1 from the regular 3 to make it never mind?
I can't. What I'm looking at is that this and this are not the same base right now.
Yeah.
Root 3 and 3 are not the same number.
Uh-huh.
But I know that root 3 is the same as 3 raised to a power.
The 1/2.
The 1/2. 3 to the 1/2 to the pi times 3 to the pi plus 3. They are now close to being on the same base.
All right, so
3
you
to
can
the
do
pi over 2.
3 to the pi over 2 plus.
Now, I want you to explain to me why it's 3 to the pi over 2 and not 3 to the pi plus a half. Go ahead, Noah.
Because it's an it's a power over power. So like if the exponent is being multiplied, how to explain this? Just
Power.
You multiply both exponents.
So this gives me this times this. When you raise a power to another power, the powers get multiplied. And now we're multiplying 2 powers with the same base. The rule there changes.
So this should be 3 to the pi plus pi over 2 plus 3, because they're not like.
And the best that we can do with this exponent, now that it's all a single exponent, is to try to do a common denominator and bring it all together. Let's at least bring those two together. This is 3 to the half pi plus 1 pi. That'd be 3 pi over 2 plus 3, and that's good enough. It's basically just adding what's 1/2 plus 1.
Is it okay if I write 3 halves pi plus 3?
That's fine.
And then that's it. That's how you figure it.
Yeah, this would be a simplified answer. Yes, Zach?
Aren't you still? Isn't it saying you're still multiplying by the same base?
We are multiplying by the same base when I go from this step here to this step there. That's a multiplying same base. And when you multiply by the same base, you add the exponents. That's not a power of powers rule. Power of powers is where I have a single base and I'm raising its multiple powers. So what's your question?
Why didn't you add those?
I did. I took pi over 2 and I added pi plus 3. That's what this step is. Then I just simplified that. Yes, Andrew?
Why do you simplify?
Well, because I have pi over 2 and pi, and I can bring those together as a single expression.
No, it's like in general, like why do you simplify that? What does it help us?
What is the purpose of simplifying?
Yeah.
In the longer sense, it's expressing things in a different form that makes it easier to work with. For things coming down the road, you want to be able to bring things together in simpler forms. One of the reasons for this is that eventually these are going to be x's in different spots, and we're going to want to be able to bring them together in order to solve them. What would this be? 3 to the root 6 times 3 to the root 6.
3 to the 2 root 6.
So I'll have people all the time tell me that that's 3 to the 6th. You're not thinking, you're not being careful with your rules. This is 3 to the root 6 plus root 6, which is a great step to show, because then the next step is 3 to the 2 root 6. You could argue that 3 to the 2 root 6 is the same as this, which is the same as 9 to the root 6, but I would actually consider this to be simpler, because it's a simpler base. And we're going to overuse the word base this year, because technically, bases themselves, like that 3, the problems become a lot easier when you work with simple bases, like 2s and 3s and 5s. Not 4s, because 4 can be made to be 2 squared. We're going to be doing a lot with bases and moving numbers so that bases are the same. Yes, no?
Would the second answer also be acceptable?
It would, but I would consider the first one to be more simple. Okay, number 5. 3 to the root 6 plus 3 to the root 6. This one's trickier.
Would that be 6 or just 2 root 6?
Be careful, because if I added x squared plus x squared, what is that?
2x.
So if I add 3 to the root 6 plus 3 to the root 6, what's that?
2 3 2 3 to the root 6.
It is 2 3 to the root 6.
Yeah, like what I just.
No, because the 2 times 3 is not 6. So this is where we have to be very, 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 very careful. Shh, hang on. Why don't I walk through a couple of reasons on this, then we'll backtrack and see if there's some questions. So when we kind of back up, what you have to keep track of is what's a coefficient, what's a base, and what's an exponent. In this problem, this right here is a base. It's not a coefficient. The coefficient is 1. And the coefficient here is 1. And so what you're saying is you have 1 3 to the root 6 plus another 3 to the root 6 gives me how many total 3 to the root 6s? 2 of them. But then you get this, which that's a better way to write it. You can't multiply the 2 times the 3 because this is 2 to the first power, and that's not really 3. That's 3 to the root 6. If you made that 6 to the root 6, you'd be saying that both the 2 and the 3 were raised to the root 6, which you don't mean. That 2 is not raised to the root 6. It's raised to the first power. So you have to leave it like that, which means you guys are going to have to get used to writing polynomials in ways you're not going to like. 2 times 7 to the x can't be simplified, much like 2x to the 7th can't be simplified. Those are 2 different versions of the same idea, coefficient, base, exponent. Yes, Noah?
Why can't you do anything with the exponent? Like why does it just say square root of 6?
Well, what would you do?
I just thought that I guess it's when you're multiplying.
Yep, it's when you're multiplying. When you're adding, again, x squared plus x squared, that gives me 2x squareds because it's the same reason. 1x squared plus 1x squared is 2x squareds. So 1 3 to the root 6 plus 1 3 to the root 6 gives me 2 3 to the root 6. Now, if I really, really, really wanted to be clever, what is 3 to the root 6 plus 3 to the root 6 plus 3 to the root 6?
3 times 3 to the root 6.
Yes, 3 times 3 to the root 6. But this can go one step further now. They are the same base.
Wait, what do you mean?
What is the rule? When you multiply the same base, what do you do to the exponents? Add them. This could be 3 to the 1 plus root 6 now. That's being clever.
And that's only if the bases are like
Only if the bases are the same. We will need to do a lot of kind of separation with bases needing to be the same and when they're not the same. A lot of that. So this is going to take some time, and I know there's going to be a lot of little minor mistakes that creep up here and there. I'm going to do a little bit of a side. Yes, John?
I just said we're going to do oopsies.
We'll have oopsies. I want to keep clear that this right here is not the same as this. This is a little bit of a kind of a note to yourself. Just like xy squared is not the same as xy quantity squared. You guys know the second one, so the first one should make sense. I also want to remind you that negative 9 to the x is not the same as negative 9 raised to the x. So let's get back to some examples, because we're going to just do a ton of minor ones that will hopefully give you some of these little details that creep up. 9 times 2 to the x. I want to simplify that as much as possible. What's this?
Squared times 2.
You could argue that. You could say, well, maybe you want a factored form, but then what do we do there? Nothing. This can't be simplified. I mean, you can factor it if you want to, but I like giving you examples that you can't do anything with. You really couldn't do anything with that. What about 9 to the x times 2 to the x?
That would be 9 times 2. No, it wouldn't.
It would.
It would?
They're both raised to the x power. So you could write it like this.
You could write it that way.
Oh, yeah.
Because both of those are being raised to exactly the same power. So I could write it as 18 to the x power. Or I would call this one the simplest exponent. You could actually make them have simpler bases. I could say this 9 could be really 3 squared, which would then be 3 to the 2x times 2 to the x. And that's not the simplest exponent, but that is the simplest basis. And my point with that is that you're going to have multiple forms of the same thing, of the same numbers, and you would actually have to know how to move them back and forth to each other. depending on what the problem might call for. Let me give you a problem that actually has a pretty straight set of directions. Simplify this to the simplest base. Actually see if you can multiply 16 times 2 to the x. There is something special about 16 that makes you able to multiply it by 2 to the x. What is special about 16? Samrawit? 16 can be substituted with 2 to the 4th. And so that gives me 2 to the 4th times 2 to the x. And now I can make that 2 to the x plus 4. Can I do a variant of this problem?
Sure you could. 32.
Guess what your most common base you're going to use is? 2. And because that's the most common base you're going to use, you're going to want to know your powers of 2. We talked about these a few times. The 2 that I would have memorized, 2 to the 6th is 64, and 2 to the 10th is 1024. Because you can work your way forwards and backwards from those to get to the other powers. What is 512? 2 to the 9th.
What?
So this is 2 to the 9th,
You meant 5 to
which means that 1 over 2 to the 9th is 2 to the negative 9.
Whoa. You expect it to be so complicated.
Well, we have to graph these.
Later. 2 to the pi times 3 to the root 5. You guys should know me well enough to know what I'm trying to point out with this one. Can't be simplified. So let's... Oh, it's a telephone game. In a telephone game, I make problems up year by year, but I look off the previous year. So every year I'm building and changing things.
So you're plagiarizing your quizzes.
Yes.
Is it because they have the same base?
It's these two?
Yeah.
They don't have the same base. Yes, that's why. If they did, you could bring them together and add them. So like 2 to the pi times 2 to the root 5, you could write as 2 to the pi plus root 5. That'd be okay. Number 12. 1/32 raised to the root 2 minus 6 over negative 64 raised to the root 2 minus 8.
Is that the grouping? Yeah.
So don't be intimidated. Don't be intimidated. Let's look at the bases. And we're going to express each of the bases. I'm going to take this little step by step. What is 32 as a power of 2? 2 to the 5th. So we're going to go 1 over 2 to the 5th. I know that negative is off to the side. 64 is 2 to the 6th. And I get to the root 2 minus 8. Now this 1 over 2 to the 5th, I could express that as 2 to the negative 5th. To the root 2 minus 6. And that is all over negative 2. And I have 6 raised to that power, so I can do power of powers, multiply the powers. 6 root 2 minus 48. And I could do the same thing. I'm going to show this off here so you guys can keep track of it. Same thing with this. I could go 2 to the negative 5 root 2 plus 30 over negative 2 root 6 minus 48. So what I have is really this. It's going to be a negative number in the end. That's what the negative that's sticking around means. But how do I bring it together? What's the rule about dividing with the same base?
You're subtracting.
Yeah. Garrett, what's the question?
So how did you get from radical 2 minus 8 for the denominator to 6 radical 2 minus 48? Like you multiply by 6.
This is a step right here, and this is a step right here. And when you raise the power to another power, the powers get multiplied. That was distributed.
I see.
So yes, we do subtract. I'm going to keep the negative because the negative is sitting out to the side. It's a negative number. 2 to the negative 5 root 2 plus 30. And when you subtract, you distribute your negative. Minus 6 root 2 plus 48.
Wait, can I ask why it would change to negative?
Why it would what?
Why would it be negative? Because
Why this would be negative?
I know, but there's a positive on top.
A positive number divided by a negative number is a negative.
You were just bringing it back up, like.
No, I'm actually pulling this out as a negative 1 and just kind of leaving the negative 1 off to the side. So we add these, we get 78 minus 11 root 2. And that's as simple as that can go.
Simple. Simple. That's simple.
Okay, keeping track of my numbering system. Number 13. This is the last simplify one before we move to some solves. 1/16 to the x plus 4 times 256 to the 2x plus 1. 1/16 is 1 over 2 to the 4th.
Whoa, what? And that would be 2 to the 8th.
256 is 2 to the 8th. Or 2 to the negative 4th. And I can distribute this 2 to the 16x plus 8 to the negative 4 minus 16 and 2 to the 16x plus 8. And 2 to the 12x minus 8. Hang on.
We should turn these in. 70 points. And you didn't come back.
Solves. 7 to the x equals 1/49. I want to do 2 problems with this, so bear with me on this. Please don't get jittery, especially in about 40 seconds here. 7 to the x equals 1/49. Your goal is to make both sides be simple bases. 7 to the x is already simple. Right side, 1 over 7 squared, or 7 to the negative 2. What does x have to be?
Negative 2.
This is a new style of solving, but it builds on things that you guys have been doing. I'm going to do one more. The cubed root of 16 raised to the x minus 2 equals 1 over 1024 raised to the x plus 1.
There's a Kairos information meeting in the chapel during this PRT.
Thank you, Bree.
If you are attending Kairos next week and have not attended a meeting, please come to this meeting.
What is 16, by the way? 2 to the 4th. So we got cubed root of 2 to the 4th to the x minus 2 equals 1 over, what is 1024? 2 to the 10th. And now keep them going. 2 to the 4th cubed root is really 2 to the 4/3 to the x minus 2. And this is 2 to the negative 10 to the x plus 1. Which means this is 2 to the 4/3 x minus 8/3, and 2 to the negative 10x minus 10. Now you can drop the bases. 4/3 x minus 8/3 has to equal negative 10x minus 10. And you're on for a regular solve from there. Multiply by 3. Add 30 to both sides. 26x, add 8 to both sides equals negative 22.
Wait, no, it'd be 30.
34, you're right. And we get x is equal to negative 11/17. So all of that is built around making both sides be the same base. Okay. Not yet. I promise I'll collect it when the sophomores get back. Right now I've got way too many gone.
1 through 30.
Oh.